Hello everybody, this is lesson 16 of the lecture International Economics. I will discuss slides 1 to 27 of chapter 3, Currency Politics. Before we start, let me give you an overview of this chapter. We will first discuss two theories which explain what factors determine the exchange rate between the currencies of two countries. One theory is called the purchasing power parity, the other theory is called the interest parity theory. We will also check the empirical performance of these theories. Then we discuss how central banks can influence the exchange rate of their currency and what consequences this can have. Finally, we will investigate some basic techniques private companies can use to hedge trade deals in foreign currencies against exchange rate risk. At the beginning, let's clarify some definitions. The foreign exchange rate of a country or currency area is the price of domestic currency in units of foreign currency. So it has the dimension foreign currency units per domestic currency. Let's make a numerical example. The exchange rate of the euro versus the dollar is currently 1.1304 dollar per euro. So 1 euro has the value of 1.1304 dollar. As a shortcut for exchange rate, we will use the following lowercase letter e. E has the dimension dollar per euro, so we will use the index symbols dollar over euro to make this clear. Following this definition, an appreciation of domestic currency means that for 1 unit domestic currency, more units of foreign currency is paid. As a result, the exchange rate gets larger. We receive more dollars for 1 euro. To the contrary, consequently, depreciation means the opposite. For 1 unit domestic currency, less units of foreign currency is paid. As a result, the exchange rate, the number of dollars we receive for 1 euro, gets smaller. Why do people demand foreign currencies? Well, all transactions recorded by the balance of payments of countries in different currency areas demand an exchange of currencies. Capital transactions typically lead to a demand for foreign currencies if domestic savers want to buy foreign securities with higher interest rates and need foreign currencies to do so. Or if, let's say, foreign investors who have received domestic currency credits with lower interest rates want to exchange them for foreign currencies. Trade in goods or services leads to a demand for foreign currency if, for example, domestic consumers want to buy foreign goods with lower prices and need foreign currencies to do so. Or another example is foreign producers who sold goods to the domestic market at higher prices and need foreign currency to pay their production factor costs at home. These considerations show that demand and supply on foreign exchange markets are influenced by two important factors: the relation between domestic and foreign prices or goods, so the price level of domestic goods versus the price level of foreign goods, and the relation between domestic and foreign interest rates. Domestic interest rates compared to the interest rates in foreign currency areas. In the following, we will study these relationships in more detail. Let's start with the relation between the exchange rate and the prices for domestic and foreign goods. We can find the accurate relation between the exchange rate and the prices for domestic and foreign goods with the help of a numerical example. Where would you buy cookies if the following exchange rate and prices are given? The price for 1 kilogram cookies in the euro area would be €1, while the price for 1 kilogram cookies in the dollar area would be $2. The exchange rate is $4 for €1. Let's assume that there are no transportation or other transaction costs. To find an answer to this question, we can simply express the prices of cookies in one currency and then compare where cookies are cheaper. Let's express the price of cookies in euro. So we know already that the price of European cookies is $1. So here we have not to make any calculations. To express the price of American cookies in euro, we have to do a simple calculation. We have to transform the dollar price of 1 kilogram cookies into the euro price. To do so, we have to divide the dollar price over this exchange rate. If you divide it, then the dollar dimension cancels and we receive a simple euro dimension of this price per kilogram. So if you fill in now our numbers in this formula, $2 for 1 kilogram American cookies, and divide this over the exchange rate, $4 for €1, we receive the euro price for 1 kilogram of American cookies, which equals €0.5. This means, of course, that the cookies in the USA are cheaper. As a result, domestic people want to buy cookies only in the USA. So the demand for dollar will grow, since they need to exchange euro into dollar to buy cookies in the USA, and this means they supply more euro to the foreign exchange market, and as a result the euro will depreciate against the dollar. So an exchange rate of $4 for €1 cannot be the equilibrium exchange rate. So let's see what would happen if we take a somewhat lower exchange rate. Let's assume the same prices again, and now an exchange rate of only $1 per euro instead of $4 per euro. What is now the price of a kilogram cookies in the euro and the dollar area? Well, the euro price of cookies in the euro area is of course not affected by this change of the exchange rate. However, we will now receive a different euro price of cookies in the dollar area. If we divide the price of cookies in the dollar area expressed in dollar over the depreciated exchange rate, we receive now a euro price for cookies in the dollar area equal to €2 per kilogram cookie. This means now, of course, that given this exchange rate, cookies are cheaper in the euro area. As a result, Americans would now like to buy cookies in the euro area. To do so, they need to exchange dollar into euro, so they would demand euro, such that the demand for euro will grow, and they will supply at the same time dollar. This would cause an appreciation of the euro against the dollar. So an exchange rate of $1 per euro can also not be the equilibrium exchange rate. The equilibrium exchange rate must lie somewhere between $1 per euro and $4 per euro. How can we find the equilibrium exchange rate? Instead of this numerical trial and error method, we can simply set up an equation that equals the price of cookies measured in euro in the euro area and the dollar area. We fill in then the numbers for the prices: $2 for 1 kilogram cookies in the United States, €1 for 1 kilogram cookies in the euro area, and leave the exchange rate as an unknown variable. We now can simply solve for the exchange rate to find the equilibrium exchange rate numerically, where this equation will hold. We can do this by multiplying both sides of the equation by the unknown exchange rate variable. Then it disappears on the left side and reappears on the right side of the equation. Then we can divide the equation over the euro price level of €1 per kilogram cookies, which does then disappear off the right side and reappears on the left side. And then we have here a numerical expression which we can easily calculate, and this expression tells us that the equilibrium exchange rate is $2 per euro. So it is in fact a number between the interval of $1 per euro and $4 per euro. At this exchange rate, the price of cookies measured in euro or in dollar is the same in both currency areas. So there will be no more pressure on the foreign exchange market to change the exchange rate. Consequently, a necessary condition for an equilibrium on the exchange market is that all goods which can be traded between two currency areas have the same price, measured in euro or measured in dollar. At this exchange rate of $2 per euro, no additional demand or supply for dollar or euro is caused on the foreign exchange market. As a result, the exchange rate has reached an equilibrium level, since it is stable. This relation is called the purchasing power parity, since the purchasing power of both currencies in real terms is the same at this exchange rate. Now we can use the purchasing power parity formula and express it in different ways. This is the way we have used so far. Here we measure the prices of goods in euro, but we can multiply this equation by the exchange rate, and then we measure the prices of goods in dollar. We can also solve for the exchange rate, and then we have the equation that gives us the value of the purchasing power parity exchange rate. Of course, this simple purchasing power parity formula does only hold for goods where transportation costs are close to zero. For most goods, this assumption is not justified. In this case, the formula must be modified to take care for transportation costs. As a result, in the presence of transportation costs, there is a band around the purchasing power parity exchange rate in which the exchange rate is not affected by the prices of goods. In reality, transport costs for most goods are between 0 and infinite. Beside transport costs, there are also other factors preventing a strict empirical validity of the purchasing power parity theorem. For example, tariffs and quantitative restrictions can also prevent trade and will therefore act like transport costs, or monopolies or oligopolies allow companies to apply profit maximizing price differentiation strategies between different currency areas, which will also prevent the purchasing power parity theorem to hold exactly. So in reality, it is very likely that a kind of bandwidth exists around the purchasing power parity exchange rate, and within this bandwidth the actual exchange rate cannot be affected by international trade. We can determine this bandwidth based on simple algebra, as the following digression shows. Let's have a look at the resulting equation of this calculation. If there are transaction costs measured by uppercase letter C in terms of dollar, the actual exchange rate is free to move between a lower and an upper border around the purchasing power parity exchange rate. The higher these transaction costs per piece, measured by uppercase letter C, the lower the effect of international trade on the exchange rate. This bandwidth gets the larger, the broader, the higher the transaction costs measured by capital letter C are. If these transaction costs go towards infinity, there will be no trade, since transaction costs are too high, and hence, in this extreme case, the exchange rate is not affected by international trade at all. If transaction costs go to zero, we have to fill in a zero here for the capital letter C variable, and then the bandwidth disappears. So we receive this equation, which implies that in this case the actual exchange rate is exactly equal to the purchasing power parity exchange rate. Of course, in reality, we can neither expect transaction costs equal to zero nor transaction costs being infinitely high. In reality, where transaction costs for most goods lie somewhere between 0 and infinity, there will be a transaction cost band around the purchasing power parity exchange rate, in which the actual exchange rate is not affected by trade. This is displayed by the following diagram for the exchange rate between the dollar and the euro. The green line represents the actual exchange rate of the euro against the dollar in terms of dollar per euro. The dashed red line represents the purchasing power parity rate of the euro against the US dollar, calculated on the basis of prices of standardized baskets of consumer goods. The transaction cost band lies, according to our formula, around the purchasing power parity exchange rate. Within this band, the actual exchange rate is not influenced by international trade, so it is undetermined within this band. In a world without transaction costs, the transaction cost band would be zero, and according to the purchasing power parity theory, the actual exchange rate would always follow the purchasing power parity exchange rate, such that the green line and the dashed red line would be identical in a world without transaction costs. This diagram shows the development of the actual exchange rate and the purchasing power parity exchange rate between the franc français and the Deutsche Mark from the year 1960 to the year 2018. The dashed red line is the logarithm of the actual exchange rate, and the continuous blue line is the logarithm of the purchasing power parity exchange rate. Both rates have the dimension Deutsche Mark per franc français, so the diagram uses the inverse dimension we have used so far. To calculate the purchasing power parity exchange rate, the bundle of goods used to measure the consumer price index is used. All values in this diagram are expressed in logarithms. The diagram reveals that until the beginning of the 90s, the French consumer price index was growing faster than the German, such that the purchasing power parity exchange rate, the blue line here, experienced a long-run downward trend. Roughly 10 years before the foundation of the European Currency Union, the relationship stabilized and the purchasing power parity displays a sideward trend along a level of 0, which corresponds to a level of 1 in delogarithmized terms. Since the beginning of the European Monetary Union in the year 1999, the nominal exchange rate between France and Germany has been fixed to a level of 1, since we use the euro as a common currency. As a result, the logarithm of the actual exchange rate equals 0. As the purchasing power parity exchange rate, the blue line, indicates the diversion of the price levels has become smaller, but there is still a small deviation which indicates that transaction costs still play a significant role. All in all, the diagram shows that the actual exchange rate, the dashed red line, followed the purchasing power parity exchange rate, the continuous blue line, in the long run. Especially in the period before the 90s, the franc français displayed a steady depreciation to compensate for the higher French inflation rates. This is exactly what the purchasing power parity theory predicts for such a case. But we also find significant deviations of both lines, for example here in this region, which indicate that transaction costs prevented a closer convergence of both variables. For other country pairs, a similar development of actual and purchasing power exchange rate is obvious. Let's finally transfer our results about the impact of goods prices on the exchange rate on a diagram of the foreign exchange market. The demand curve for euro has a negative slope because the cheaper the euro, the cheaper are goods from the euro area for foreigners. If foreigners want to buy more goods from the euro area, they will have to exchange dollars and euro. So the euro demand increases as the euro gets cheaper. The supply curve for euro has a positive slope because the more expensive the euro, the cheaper are goods from the USA for domestic consumers. If domestic consumers want to buy more goods from the USA, they will have to exchange more euros in dollars. So the euro supply increases as the euro gets more expensive. On the market where the euro is traded for dollar, we measure the exchange rate on the y-axis in terms of dollar per euro as usual, and the volume of traded euros on the x-axis. The euro demand curve has the usual negative slope as we have just seen. The less dollar has to be paid for 1 euro, the more euro goods are cheaper than dollar goods, and the more euro is demanded in exchange for dollar. The euro supply curve has the usual positive slope as we have just seen, since the more dollar is paid for 1 euro, the more US goods are cheaper than euro goods, and the more euro is hence supplied in exchange for dollar. The intersection point of both curves provides, as usual, the equilibrium exchange rate. What happens now to the equilibrium exchange rate if inflation in the USA is, let's say, higher than inflation in the euro area? Prices for goods do not appear on the x-axis. Hence, these prices are shift parameters. If goods in the USA become more expensive, Americans will try to buy more goods in the euro area, where prices are now cheaper. Consequently, the demand curve for euro shifts upward or to the right if the prices in the US get higher. Since less Europeans want to buy goods in the USA because US prices are now more expensive, Europeans demand less dollar and hence supply less euro to the foreign exchange market. Consequently, the euro supply curve shifts to the left. As a result, the euro appreciates against the dollar. The new intersection point lies here on a higher level as before. So this graphical analysis comes to the same result as the purchasing power parity equation. If in the USA the inflation rate is higher than in the euro area, the euro appreciates against the dollar. If the opposite would be the case, the euro would depreciate against the dollar. So let's sum up our results. International trade in goods causes the exchange rate to adjust for inflation differentials between two countries. If inflation in the USA is higher than inflation in the euro area, the exchange rate of the euro against the dollar will appreciate. If inflation in the USA is lower than inflation in the euro area, the euro exchange rate against the dollar will depreciate. So much for this lecture. In the next lecture, we will analyze the influence of differences in interest rates on the exchange rate.